Welcome to the Deep Dive. We're here to cut through the clutter and deliver the core insights you need. Today, we're diving deep into a fundamental topic: matter in our surroundings.
That's right.
Our goal is pretty straightforward: to really unpack the essential concepts about matter, drawing directly from our source material. This should give you a rock-solid understanding, perfect for your exams, yes, but also just for grasping the world.
Absolutely. And let's start right at the beginning. Fundamentally, everything in this universe, everything you can touch or sense, is made up of material that scientists have named matter.
Everything.
Pretty much everything. The air we breathe, the food we eat, stones, clouds, stars, plants, animals, even a tiny drop of water or a single grain of sand. It's all matter.
Okay, so what makes something matter?
Two key things. It
Yeah.
has to occupy space. That's what we call volume. And it has to have mass. These are the defining properties.
Mass and volume, got it.
And in science, we have standard units for these. Mass is measured in kilograms, kilogram. Volume, the SI unit, is the cubic meter, M. Though you'll often see volume, especially for liquids, measured in liters, L. 1 liter is actually a cubic decimeter, or 1,000 milliliters, which is 1,000 cubic centimeters.
Useful conversions to remember.
Definitely. And, humans have thought about this for ages. Early Indian philosophers classified matter into 5 basic elements, the Panchtattva.
Yes. Air, earth, fire, sky, and water.
Exactly. They believed everything, living or non-living, was made of these. Ancient Greek philosophers, interestingly, had very similar ideas.
It's fascinating how different cultures arrived at similar concepts.
It is. Modern science, of course, classifies matter based on its physical properties and its chemical nature. For this deep dive, we're really going to focus in on the physical properties.
Right, so if everything's matter and it has mass and volume, the big question is, what is it actually made of? I know there was a long debate about this.
There was indeed. For a long time, 2 schools of thought existed. One believed matter was continuous, like a solid block of wood, no gaps, just uniform stuff.
Like a smooth, unbroken thing.
Exactly. The other school proposed that matter was made up of particles, tiny individual bits, almost like sand.
So, continuous versus particulate. How did we figure out which was right?
Through observation and simple experiments. Think about activity 1.1 in the source material dissolving salt or sugar in water.
Okay.
Take a beaker of water, note the level carefully. Then you stir in some salt or sugar until it dissolves. What do you observe?
The salt seems to disappear, and the water level. It doesn't really change much, does it?
Precisely. If water were continuous, adding salt should have raised the level noticeably. The fact that it doesn't implies that the salt particles are spreading out and fitting into the tiny spaces between the water particles.
So the water isn't a solid block, it has gaps.
Exactly. This simple experiment provides strong evidence that matter is made up of particles, not continuous. It's particulate.
That makes sense. So particles it is. Just how small are these particles then? Are we talking microscopic?
Oh, much, much smaller than microscopic. They are, as the text says, small beyond our imagination. Really incredibly tiny.
Wow. How can we even demonstrate that?
Well, activity 1.2 gives us a clue. Take just 2 or 3 crystals of potassium permanganate. That chemical gives a strong purple color. Dissolve them in, say, 100 milliliters of water.
Okay, the water turns purple.
Right. Now take just 10 milliliters of that purple solution and add it to another 90 milliliters of clear water. So you're diluting it tenfold.
It'll still be colored, but fainter.
Exactly. And you can repeat this process. Take 10 milliliters of the diluted solution, add it to 90 milliliters clear water again and again, maybe 5 to 8 times. Even after all those dilutions, the water often still shows a faint color.
So that tiny initial amount contained enough particles to color a huge volume of water.
Precisely. Or think about Dettol. You can do the same with its smell. A tiny amount can be detected even after repeated dilutions. It tells us that just a few crystals, or a small drop, must contain millions and millions of these incredibly tiny particles which keep spreading out.
Small beyond imagination. Okay, so matter is particulate, particles are tiny. What else characterizes them? You mentioned spaces between them earlier.
Yes, that's the first key characteristic.
Yeah.
Particles of matter have space between them. We just saw that with the salt dissolving in water, right?
Right, fitting into the gaps.
And the potassium permanganate spreading out. It's the same reason when you make tea or coffee or lemonade, the particles of, say, sugar or lemon juice distribute evenly throughout the water. They mix because they can move into the spaces between the water particles.
Okay, so spaces exist. What about the particles themselves? Are they just sitting still in the spaces?
No, definitely not. That's the second key characteristic. Particles of matter are continuously moving. They aren't static at all.
Continuously moving. How so?
They possess what we call kinetic energy. Because they have this energy, they're always in random motion. And crucially, this kinetic energy increases as the temperature goes up.
So hotter means faster movement.
Exactly. More heat, more kinetic energy, faster particle movement. Think about an unlit incense stick in agar body. You have to get quite close to smell it, right?
Yes.
But light it, and the heat causes the particles making up the fragrance to gain energy, move much faster, mix with the air, and spread out, so you can smell it from across the room.
Okay, that makes sense. The heat spreads the smell.
It does. Or consider activity 1.4, dropping ink versus honey into water. When the ink spreads out, it diffuses much faster than the honey. The particles are moving at different rates.
And temperature affects this diffusion rate.
Absolutely. Activity 1.5 shows this clearly. If you put a crystal of copper sulfate or potassium permanganate into a glass of hot water and another into cold water, you'll see the color spread much more quickly in the hot water.
Because the particles have more kinetic energy.
Precisely. They move faster, mix faster. This intermixing of particles of different types of matter on their own is called diffusion. And yes, heating speeds up diffusion because the particles are simply moving faster and have more energy to mingle.
Okay, so they have space, they're moving constantly. Is there anything holding them together or keeping them apart?
Good question. There is indeed a force involved. The third characteristic is that particles of matter attract each other.
They attract, so they don't just fly off completely.
Well, they do in gases to a large extent, but there's always some force of attraction. The strength of this force varies hugely. Think about activity 1.6, the human chains.
Right, holding hands versus just fingertips.
Exactly. If people link arms tightly, like traditional Idu Mishmi dancers, the chain is very strong, hard to break. If they just touch fingertips, it's very easy to break. It illustrates that the force of attraction can be strong or weak.
So how does this apply to matter?
Think about activity 1.7, trying to break an iron nail, a piece of chalk, and a rubber band. The iron nail is incredibly hard to break, right?
Yeah.
Chalk breaks much more easily, and a rubber band stretches but eventually snaps. This tells you the particles in the iron nail are held together by a much stronger force of attraction than those in chalk or rubber.
I see. Different materials, different stickiness between particles?
Sort of, yes.
Yeah.
Or activity 1.8, try cutting through the surface of water with your finger. The water parts, but it immediately flows back together. That surface tension is due to the force of attraction between water particles pulling them together.
Okay.
So the takeaway is, particles attract each other, but the strength of this attraction is different for different kinds of matter.
Right. So tiny moving particles with spaces attracting each other with varying strength. How does this explain the different states of matter we see, like solids, liquids, and gases?
Exactly. Those three characteristics, the space, the movement, and the attraction, are precisely what determine the state. Matter exists in these different states because of the variations in these characteristics of the particles.
Okay, let's break those down, starting with solids.
Right, the solid state. Think about common solids, a pen, a book, a needle, a piece of wood, like in activity 1.9. What do they have in common?
They have a definite shape. A pen is always pen-shaped. And a fixed volume.
Exactly. Definite shape, distinct boundaries, fixed volume. They're also very difficult to compress. We say they have negligible compressibility. They strongly resist changes to their shape. They're rigid.
But what about something like a rubber band? It changes shape when you stretch it.
Good point. A rubber band does change shape under force, but it regains its shape when the force is removed. That ability to regain shape is characteristic of solids. If you apply too much force, it breaks. Again, typical solid behavior. So yes, it's a solid.
Okay. And sugar or salt? They take the shape of the jar you put them in.
But think about an individual crystal of sugar or salt. It has a fixed shape, right?
Yeah.
A tiny cube or whatever form it takes. The collection of crystals takes the shape of the jar, but the individual particles, the crystals themselves, retain their shape. So, still solid.
I see the distinction. What about a sponge? You can compress it easily.
True, but a sponge is a solid with tiny holes, pores, throughout it. These holes are filled with air. When you press the sponge, you're actually expelling the air trapped in those holes. The solid material itself isn't being compressed much. It's the air escaping that allows it to be squeezed. Once you release it, it usually springs back.
Okay, so solids are defined by tightly packed particles, strong attraction, keeping them in fixed positions with a definite shape and volume. What about liquids then?
Let's move to the liquid state. Collect some liquids, water, oil, milk, juice, and pour them into different shaped containers, like in activity 1.0. What's the key observation?
They take the shape of the container, no fixed shape.
Precisely. Liquids have no fixed shape, but they do have a fixed volume. If you pour 100 milliliters of water from a beaker into a flask, it's still 100 milliliter.
Right. Fixed volume, but takes the container shape.
And they flow. Liquids can be poured, they change shape easily. We call this property fluidity. They are not rigid like solids.
And diffusion happens in liquids too, right? You mentioned ink spreading in water.
Yes, and importantly, solids and gases can diffuse into liquids. Think about aquatic live fish. Fish breathe oxygen that's dissolved in the water. That oxygen is a gas that is diffused from the air into the water. Same for carbon dioxide needed by aquatic plants.
That's vital. Is diffusion faster in liquids than solids?
They're much faster. In liquids, the particles are still quite close, but they aren't held in fixed positions like solids. They can move around, slide past each other, and there's more space between them compared to solids. This freedom of movement and greater spacing allows for a higher rate of diffusion.
Makes sense. Particles can move more freely. Okay, that leaves gases.
The gaseous state. Think about activity 1.11 using syringes. If you try to compress air, water, and maybe chalk powder in separate syringes with the nozzle blocked.
The air compresses easily, the water barely at all, and the chalk, well, it's a solid, so not really.
Exactly. Gases are highly compressible compared to solids and liquids. This is a defining feature. It's why we can store large amounts of gas in relatively small cylinders. Think of LPG cylinders for cooking, oxygen cylinders in hospitals, or CNG uses fuel in vehicles. Huge volumes of gas are squeezed into those tanks under pressure.
That high compressibility is very practical. What else? You mentioned the smell of food spreading quickly.
Right. That points to another key property, rapid diffusion.
Yeah.
In the gaseous state, particles move randomly at very high speeds, and the spaces between them are much, much larger than in solids or liquids.
So they just zip around and mix quickly?
Pretty much. That high speed and large intermolecular space allow gases to diffuse very rapidly and fill whatever container they are in completely. This constant high-speed random motion also explains gas pressure. The particles are constantly colliding with each other and, importantly, with the walls of the container.
Ah, like tiny balls bouncing off the side.
Exactly. The force exerted by these gas particles per unit area on the walls of the container is what we measure as pressure.
Okay, solids, liquids, gases defined by particle spacing, movement, and attraction. Now, can matter actually change from one state to another? We see it all the time with water ice, liquid water, steam.
Absolutely. Matter can transition between these states. Water is the perfect everyday example. And the key factors driving these changes are temperature and pressure. Let's start with the effect of change of temperature.
Heating things up or cooling them down.
Precisely. Consider activity 1.112. Heating ice. You start with solid ice. As you supply heat energy, what happens to the particles?
They get more kinetic energy, right? Start vibrating more.
Exactly. The increased temperature boosts their kinetic energy. They vibrate more and more vigorously. Eventually, they gain enough energy to overcome the strong forces of attraction holding them in their fixed solid positions.
And they start to move around more freely.
Yes, they break free from the rigid structure, and the solid melts into a liquid. The specific temperature at which this happens, at standard atmospheric pressure, is called the melting point. For ice, that's 0 degrees Celsius or 273.15 Kelvin. This process of solid turning into liquid is also called fusion.
Okay, melting point, fusion. Simple enough.
But here's something really interesting. While the ice is melting, if you keep monitoring the temperature, you'll find it stays constant at 0 degrees C, even though you're continuously adding heat.
Stays constant. Where's the heat energy going then?
It's being used to break those bonds, to overcome the forces of attraction holding the ice particles together. This energy gets absorbed by the particles without increasing their kinetic energy, and thus temperature. It's hidden energy, so we call it the latent heat of fusion.
Latent means hidden. So it's the heat needed just for the change of state itself.
Exactly. It's the amount of heat energy required to change 1 kilogram of solid into liquid at its melting point without any change in temperature. This means, and this is important, particles in water at 0 degrees C actually have more energy than particles in ice at the same temperature, 0 degrees C, because they've absorbed that latent heat.
That's a key difference. Okay, so the ice is melted. What happens if we keep heating the water?
The water particles gain more kinetic energy, move even faster. As you continue heating, more and more particles gain enough energy to escape from the surface. Eventually, you reach a temperature where particles throughout the bulk of the liquid have enough energy to break free from the forces of attraction completely and change into the gaseous state, or vapor.
That sounds like boiling.
It is. The temperature at which a liquid starts boiling at atmospheric pressure is its boiling point. For water, that's 100 degrees C, or 373 Kelvin. Boiling is called the bulk phenomenon because bubbles of vapor form throughout the liquid, not just at the surface.
And is there a latent heat involved here too?
Yes, absolutely. Similar to melting, during boiling, the temperature remains constant at the boiling point until all the liquid is turned into gas. The heat energy supplied during this phase change is used to overcome the forces of attraction in the liquid state entirely. This is called the latent heat of vaporization.
So steam at 100 degrees C has more energy than water at 100 degrees.
Significantly more, due to that absorbed latent heat of vaporization. It's why steam burns can be much more severe than burns from boiling water at the same temperature.
Good point. And you mentioned Kelvin. That's the SI unit for temperature.
Yes. For calculations, Kelvin K is standard. The conversion is simple: Kelvin Celsius plus 273 and Celsius Kelvin 273. For most day-to-day purposes, we use 273, although 273.15 is more precise. So changing temperature is clearly a major way to change the state of matter.
Definitely. Melting, boiling. Are there cases where matter skips the liquid state entirely, goes straight from solid to gas?
Yes, there are. This process is called sublimation. Some substances, when heated, change directly from solid to gas without ever becoming liquid.
Like dry ice.
Dry ice is a classic example, yes. Also, things like camphor or naphthalene balls, which you might use to protect clothes. If you heat camphor gently, like in Activity 1.13, you'll see it turn into vapor directly.
And the reverse. Gas, straight to solid.
That's called deposition. Frost forming on a cold window pane on a winter morning is an example. Water vapor in the air turning directly into solid ice crystals.
Sublimation and deposition. Okay, so temperature is key. What about pressure? You mentioned it briefly with gases. Does pressure affect state changes too?
It absolutely does. Pressure is the other major factor. We already saw how applying pressure helps liquefy gases. If you increase the pressure on a gas, you force the particles closer together.
Reducing the space between them.
Exactly. If you reduce the space and reduce the temperature, which lowers their kinetic energy, the attraction between particles can become strong enough for the gas to turn into a liquid.
So high pressure and low temperature can liquefy gases.
Correct. And solid carbon dioxide, or dry ice, is a prime example of pressure's role. It's solid CO2 stored under very high pressure. If you decrease the pressure back to normal atmospheric pressure, 1 atmosphere, it doesn't melt into liquid CO2. Instead, it sublimates directly into gaseous CO2.
That's why it's dry ice, no messy liquid phase.
Precisely. So it's clear that both pressure and temperature together determine the state of a substance. You can often achieve a state change by altering one or both.
That diagram showing solid, liquid, gas regions based on temperature and pressure really brings it together. Okay, we've covered melting, boiling, sublimation. But what about everyday things like wet clothes drying or a puddle disappearing on a sunny day? The water isn't boiling, is it?
No, it's definitely not boiling.
Yeah.
That phenomenon is evaporation. It's the change of a liquid into vapor at any temperature below its boiling point.
Below boiling point, how does that happen then?
Evaporation is a surface phenomenon. Within a liquid, particles are moving at different speeds. Some particles at the surface happen to have higher kinetic energy than others.
Just by random chance?
Essentially, yes, due to collisions and energy exchange. If a surface particle has enough kinetic energy to overcome the forces of attraction from its neighbors in the liquid, it can escape into the air as vapor. This can happen even at room temperature.
Ah, so it's just the faster ones at the surface breaking away.
That's the idea. And several factors influence how quickly this happens, as shown in Activity 1.13.
Like what makes clothes dry faster?
Exactly. First, increase of surface area. If you spread clothes out, they dry faster than if they're bunched up, right?
Yeah.
More surface means more particles are exposed and can escape.
Makes sense.
Second, increase of temperature. Even below boiling, higher temperature means more particles overall have enough kinetic energy to escape, so evaporation is faster on a warm day.
Okay. Surface area, temperature. What else?
Third, decrease in humidity. Humidity is the amount of water vapor already in the air. If the air is very humid, it's already holding a lot of water vapor, so it's harder for more water to evaporate into it. Dry air means faster evaporation.
Right, clothes dry slower on humid days.
Precisely. And fourth, increase in wind speed. Wind blows away the water vapor particles that have just evaporated from the surface. This prevents the air near the surface from becoming saturated and allows more evaporation to occur. That's why clothes dry faster on a windy day.
Surface area, temperature, low humidity, wind.
Got it.
Now, I've always noticed that evaporation seems to cause cooling, like feeling cold after getting out of a pool or when sweat dries. Why is that?
That's the very important consequence. Evaporation causes cooling. Remember those surface particles escaping? To break free from the liquid, they need energy specifically, the latent heat of vaporization.
Where do they get that energy from?
They absorb it from their immediate surroundings, which could be the rest of the liquid or the container or even your skin. When these high-energy particles leave, the average energy of the remaining particles decreases.
So the remaining liquid gets cooler.
Exactly. The liquid loses energy to the escaping particles, and its temperature drops. This absorption of energy from the surroundings makes the surroundings cooler.
Can you give some examples?
Sure. Put a drop of acetone or nail polish remover or even perfume on your palm. It evaporates quickly, and your palm feels distinctly cool, right?
Yes, very noticeably.
That's because the evaporating liquid is drawing heat energy directly from your skin. Or think about people sprinkling water on their roofs or the ground on a hot summer evening. The evaporating water absorbs a large amount of heat from the surface, making it cooler.
Like nature's air conditioning.
In a way, yes. And why do we wear cotton clothes in summer? Cotton is good at absorbing sweat. It then exposes that sweat to the air, allowing it to evaporate easily. As the sweat evaporates, it takes heat from our body, helping us feel cool.
Ah, that's the science behind it.
It is. Another great example is the earthen pot, the matka. They have tiny pores. Water seeps through these pores to the outer surface and evaporates continuously. This evaporation draws heat from the water inside the pot, making it cool.
Simple but effective technology.
Indeed. And one last common observation. Why do you see water droplets forming on the outside of a glass containing ice-cold water?
Is that condensation?
Exactly. It's not water leaking out. The air around us always contains some water vapor. When this vapor comes into contact with the very cold outer surface of the glass, the vapor particles lose energy, slow down, and change back into the liquid state they condense onto the glass.
So evaporation is liquid to gas, condensation is gas to liquid.
Precisely. Both involve energy exchange and demonstrate the constant interplay between matter and energy.
This has been incredibly clarifying. We've gone from the basic definition of matter right down to the particle level, their tiny size, constant motion, the spaces between them, the forces attracting them, and then seeing how these characteristics explain solids, liquids, gases, and all the fascinating ways they change state through temperature, pressure, and processes like evaporation. Understanding this is just fundamental for exams and for, well, understanding everything.
It really is. These aren't just abstract concepts. They explain why water boils, why perfume spreads, why sweating cools us down. Thinking about the why at the particle level really builds that strong foundation in science. It encourages you to look at the world and ask, what are the particles doing?
A great way to think about it. Keep asking why. Well, that wraps up our deep dive for today. Stay tuned for more exam-ready insights and clear explanations. In this deep dive, we covered the following topics: definition and classification of matter, physical nature of matter, particulate nature, characteristics of matter particles, space, movement, attraction, states of matter, solid, liquid, gas, and their properties, effective temperature on state change, melting, boiling, latent heat, sublimation, deposition, effective pressure on state change, liquefaction, dry ice, evaporation and its factors, how evaporation causes cooling,